Chapter 4, Fluid Kinematics. Objective. When you finish reading this chapter, you should be able to understand the role of the material derivative in transforming between Lagrangian and Eulerian descriptions, distinguish between various types of flow visualizations and methods of plotting the characteristics of a fluid flow, appreciate the many ways that fluids move into form, distinguish between rotational and irrotational regions of flow based on flow property vorticity, understand the usefulness of the Reynolds transport theorem. Fluid kinematics deals with describing the motion of fluids without necessarily considering the forces and moments they cause motion. In this chapter, we introduce several kinematic concepts related to flowing fluids. We discuss the material derivative and its role in transforming the conservation equations from Lagrangian descriptions of fluid flow, flowing a fluid particle, to the Eulerian description of fluid flow pertaining to a flow field. We then discuss various ways to visualize flow fields, streamlines, streak lines, path lines, timelines, optical methods, and surface methods, and we describe 3 ways to plot flow data: profile plots, vector plots, and contour plots. We explain the 4 fundamental kinematic properties of fluid motion and deformation: rate of translation, rate of rotation, linear strain rate, and shear strain rate. The concepts of vorticity, rotationality, and irrotationality in the fluid flows are then discussed. Finally, we discuss the Reynolds transport theorem, emphasizing its role in transforming the equations of motion from those following a system to those pertaining to fluid flow into and out of a control volume. The analogy between material derivative for infinitesimal fluid elements and Reynolds transport theorem for finite control volumes is explained. Satellite image of a hurricane near Florida coast. Water droplets move with the air, enabling us to visualize the counterclockwise swirling motion. However, the major portion of the hurricane is actually irrotational, while only the core, the eye of the storm, is rotational. Lagrangian and Eulerian descriptions. The subject called kinematics concerns the study of motion. In fluid dynamics, fluid kinematics is the study of how fluids flow and how to describe fluid motion. From a fundamental point of view, there are 2 distinct ways to describe motion. The first and most familiar method is the one you learned in high school physics: to follow the path of individual objects. For example, we have all seen physics experiments in which a ball on a pool table or a puck on an air hockey table collides with another ball or puck, or with the wall, figure 4.1. With a small number of objects, such as billiard balls on a pool table, individual objects can be tracked. Newton's laws are used to describe the motion of such objects, and we can accurately predict where they go and how momentum and kinetic energy are exchanged from one object to another. The kinematics of such experiments involve keeping track of the position vector of each object and the velocity vector of each object as functions of time, figure 4.2. In the Lagrangian description, we must keep track of the position and velocity of individual particles of fluid motion. When this method is applied to a flowing fluid, we call it the Lagrangian description of fluid motion, after the Italian mathematician Joseph Louis Lagrange, 1736 to 1813. Lagrangian analysis is analogous to the closed system analysis that you learned in thermodynamics. Namely, we follow a mass of fixed identity. The Lagrangian description requires us to track the position and velocity of each individual fluid parcel, which we refer to as a fluid particle, and take to be a parcel of fixed identity. As you can imagine, this method of describing motion is much more difficult for fluids than for billiard balls. First of all, we cannot easily define and identify fluid particles as they move around. Secondly, A fluid is a continuum with a macroscopic point of view, so interactions between fluid particles are not as easy to describe as are interactions between distinct objects like billiard balls or air hockey pucks. Furthermore, the fluid particles continually deform as they move in the flow. From a microscopic point of view, a fluid is composed of billions of molecules that are continuously banging into one another, somewhat like billiard balls, but with the task of following even a subset of these molecules is quite difficult, even for our fastest and largest computers. Nevertheless, there are many practical applications of the Lagrangian description, such as the tracking of passing scalars in a flow to model contaminant transport, rarefied gas dynamics, calculations concerning re-entry of a spaceship into the Earth's atmosphere, and the development of flow visualization and measurement systems based on particle tracking, as discussed in Section 4-2. A more common method of describing fluid flow is the Eulerian description of fluid motion, named after the Swiss mathematician Leonhard Euler, 1707 to 1783. In the Eulerian description of fluid flow, a finite volume called a flow domain or control volume is defined, through which flow flows in and out. Instead of tracking individual fluid particles, we define field variables, functions of space and time, within the control volume. The field variable, at a particular location, at a particular time, is the value of the variable for whichever fluid particle happens to occupy that location at that time. For example, the pressure field is a scalar field variable. For general unsteady three-dimensional fluid flow in Cartesian coordinates, the pressure field is equal to pressure equal to P of x, y, z, and t, equation 4-1. We define the velocity field as a vector field variable in similar fashion. Velocity field, v, equals to v as a function of x, y, z, and t, equation 4-2. Likewise, the acceleration field is also a vector field variable. Acceleration field, a, is equal to a as a function of x, y, z, and t, equation 4-3. Collectively, these and other field variables define the flow field. The velocity field of equation 4-2 is expanded into Cartesian coordinates x, y, z, or I, j, and k, as the velocity field u, v, w is equal to u as a function of x, y, z, t, I hat, plus v, x, y, z, t, j, plus w, x, y, z, t, k. A similar expression can be performed for the acceleration field of equation 4-3. In the Eulerian description, all such field variables are defined at locations x, y, z in the control volume and at an instant in time t, figure 4-3. Figure 4-3, in the Eulerian description, we define field variables such as the pressure field and the velocity field at any location and instant in time. B, for example, the airspeed probe mounted under the wing of an airplane measures the airspeed at that location. The difference between these two descriptions is made clearer by imagining a person standing beside a river measuring its properties. In the Lagrangian approach, he throws in a probe that moves downstream with the water. In the Eulerian approach, he anchors the probe at a fixed location in the water. While there are many occasions in which the Lagrangian description is useful, the Eulerian description is often more convenient for fluid mechanics applications. Furthermore, the experimental measurements are generally more suited to the Eulerian description. In a wind tunnel, for example, velocity or pressure probes are usually placed at a fixed location in the flow, measuring velocity as a function of x, y, z, and t, or pressure as a function of x, y, z, and t. However, whereas the equations of motion in the Lagrangian description following individual fluid particles are well known, for example Newton's second law, the equations of motion of fluid flow are not so readily apparent in the Eulerian description, and we must be careful to derive them. We do this for control volume integral analysis via the Reynolds transport theorem at the end of this chapter. We derive the differential equations of motion in Chapter 9. Example 4-1. A steady two-dimensional velocity field. A steady incompressible two-dimensional velocity field is given by equation 1. Velocity is equal to u, comma v, which is equal to 0.5 plus 0.8x in the I direction plus 1.5 minus 0.8y in the j direction, where x and y coordinates are in meters and the magnitude of velocity is in meters per second. A stagnation point is defined as a point in the flow field where the velocity is zero. A. Determine if there are any stagnation points in this flow field, and if so, where. B. Sketch velocity vectors at several locations in the domain between x equals minus 2 meters to 2 meters and y equals 0 meters to 5 meters. Qualitatively describe the flow field. For the given velocity, the locations of stagnation points are to be determined. Several velocity vectors are to be sketched and the velocity field is to be described. Assumptions. The flow is steady and incompressible. The flow is two-dimensional, implying no z component of velocity and no variation of u or v in the z direction. Analysis. A. Since the velocity is a vector, all its components must equal 0 in order for the velocity itself to be 0. Equation 4-4 and setting equation 1 equal to 0, the stagnation point occurs when u is equal to 0.5 plus 0.8x equal to 0, which gives a result x equal to negative 0.625 meters, and v equal to 1.5 plus 0.8y equal to 0, which gives a y value of 1.875 meters. So yes, there is one stagnation point located at x equal to negative 0.625 meters and y equal to 1.875 meters. The x and y components of velocity are calculated from equation 1 for several x and y locations in the specified range. For example, at the point x equal to 2 meters, y equal to 3 meters, u is equal to 2.1 meters per second and v is equal to negative 0.9 meters per second. The magnitude of velocity, the speed at this point, is 2.2 meters per second. At this and at an array of other locations, the velocity vector is constructed from its two components, the results of which are shown in figure 4-4. The flow can be described as stagnation point flow, in which flow enters from the top and bottom and spreads out to the right and left, about a horizontal line of symmetry at y equals 1.875 meters. The stagnation point of part A is indicated by the blue circles in figure 4-4. If we look only at the shaded portion of figure 4-4, this flow field models a convergent accelerating flow from left to right. Such a flow might be encountered, for example, near the submerged bell mouth inlet of a hydroelectric dam. The usual portion of the given velocity field may be thought of as the first-order approximation of the shaded portion of the physical flow field in figure 4-5. The flow field near the bell mouth inlet of a hydroelectric dam, a portion of the velocity field of example 4-1, may be used as a first-order approximation of this physical flow field. The shaded region corresponds to that of figure 4-4. Figure 4-4. Velocity vectors, blue hours, for the velocity field of example 4-1. The scale is shown by the top arrow, and the solid black curves represent the approximate shapes of some streamlines based on the calculated velocity vectors. The stagnation point is indicated by the blue circle. The shaded region represents a portion of the flow field that can be approximate flow into an inlet, figure 4-5. Acceleration field. As you should recall from your study of thermodynamics, the fundamental conservation laws, such as conservation of mass and the first law of thermodynamics, are expressed for a system of fixed identity, also called a closed system. In cases where analysis of a control volume, also called an open system, is more convenient than system analysis, it is necessary to rewrite these fundamental laws into forms applicable to the control volume. The same principle applies here. In fact, there is a direct analogy between systems versus control volumes in thermodynamics and Lagrangian versus Eulerian descriptions in fluid dynamics. The equations of motion for fluid flow, such as Newton's second law, are written for a fluid particle, which we also call a material particle. If we were to follow a particular fluid particle as it moves around in the flow, we would be employing the Lagrangian relationship, and the equations of motion would be directly applicable. For example, we would define the particle's location in space in terms of a material position vector, x subparticle of t, y subparticle of t, z subparticle of t. However, some mathematical manipulation is then necessary to convert the equations of motion into forms applicable to the Eulerian description. Consider, for example, Newton's second law applied to our fluid particle. Newton's second law is equation 4-5. The force of a particle is equal to mass of the particle times the acceleration of the particle, where the vector force of the particle is the net force acting on the fluid particle, m particle is its mass, and the vector acceleration particle is its acceleration. Figure 4-6. Newton's second law applied to a fluid particle. The acceleration vector is in the same direction as the force vector, but the velocity vector may act in a different direction. However, at any instant in time, the velocity of the particle is the same as the local value of the velocity field at that location. X subparticle sub t, y subparticle of t, z subparticle of t of the particle, since the fluid particle moves with the fluid by definition. In other words, the velocity vector of the particle with time is equal to the velocity vector of x subparticle t, y subparticle t, z subparticle t for a given time. To take the time derivative of equation 4-6, we must therefore use the chain rule, since the dependent variable, v, is a function of four independent variables, x subparticle, y subparticle, z subparticle, and t subparticle. Which gives equation 4-7. In equation 4-7, delta is the partial derivative operator and d is the total derivative operator. Consider the second term on the right-hand side of the equation. Since the acceleration is defined as that following a fluid particle, the Lagrangian description, the rate of change of the particle's x position with respect to time is dx particle dt equal to u. Figure 4-7, where u is the x component of velocity vector defined by equation 4-4. Figure 4-7, when following a fluid particle, the x component of the velocity u is defined as dx particle dt. Similarly, v is equal to dy particle dt, and w is equal to dz particle dt. Movement is shown here only in two directions for simplicity. Similarly, dy particle dt equals v and dz particle dt equals w. Furthermore, at any instant in time under consideration, the material position vector x particle, y particle, z particle of the fluid particle in the Lagrangian frame is equal to the position vector x, y, z in the Eulerian frame. Equation 4-7 thus becomes equation 4-8. Where we have also used the obvious fact that dt equals 1. Finally, at any instant in time, the acceleration field of equation 4-3 must equal the acceleration of the fluid particle that happens to occupy that location, x, y, and z, at that time. Why? Because the fluid particle is by definition accelerating with the fluid flow. Hence, we may replace the vector acceleration of the particle with the vector acceleration x, y, z, and t in equation 4-7 and 4-8 to transform from the Lagrangian to the Eulerian frame of reference. In vector form, equation 4-8 is written as acceleration of a fluid particle expressed as a field variable, equation 4-9. The acceleration vector as a function of x, y, z, and t is equal to d velocity vector dt, which is equal to the partial derivative of the velocity vector over the partial derivative of t, plus the velocity vector times the dot product of delta operator times the velocity vector, where delta is the gradient operator or del operator, a vector operator that is defined in Cartesian coordinates as the gradient or del operator given in equation 4-10. The gradient or del operator is equal to the partial derivative over partial derivative x, comma, partial derivative over partial derivative of y, comma, partial derivative over partial derivative of z, equal to I hat partial derivative over partial derivative of x plus j hat partial derivative over partial derivative of y plus k hat partial derivative over partial derivative of z. In the Cartesian coordinates, then, the components of the acceleration vector are acceleration in the x direction is equal to du dt plus u du dx plus v partial derivative u over dy plus w partial derivative u over partial derivative z for the x, y, and z directions. The first term on the right-hand side of the equation 4-9, the partial derivative of the velocity vector over the partial derivative of time, is called the local acceleration and is non-zero only for unsteady flows. The second term, the del operator times the velocity vector, the dot product of the velocity vector and the del operator times the velocity vector, is called the advective acceleration, sometimes the convective acceleration. This term can be non-zero even for steady flows. It accounts for the effect of fluid particles moving, advecting, or convecting to a new location in the flow, where the velocity field is different. For example, consider steady flow of water through a garden hose nozzle. We define steady in the Eulerian frame of reference to be when properties at any point in the flow field do not change with respect to time. Since the velocity at the exit of the nozzle is larger than that at the nozzle entrance, fluid particles clearly accelerate, even though the flow is steady. The acceleration is non-zero because of the advective acceleration terms in equation 4-9. Note that while the flow in the steady from the point of view of a fixed observer in the Eulerian frame of reference, it is not steady from the Lagrangian reference frame, moving with a fluid particle that enters the nozzle and accelerates as it passes through the nozzle. Example 4-2. Acceleration of a fluid particle through a nozzle. Nadine is washing her car, using a nozzle similar to the one sketched in figure 4-8. Flow of water through the nozzle of a garden hose illustrates that fluid particles accelerate even in steady flow. In this example, the exit speed of the water is much higher than the water speed in the hose, implying that fluid particles have accelerated even though the flow is steady. The nozzle is 3.9 inches long, with an inlet diameter of 0.420 inches and an outlet diameter of 0.182. See figure 4-9, flow of water through the nozzle. The volume flow rate through the garden hose and through the nozzle is 0.841 gallons per minute, and the flow is steady. Assume the magnitude of the acceleration of a fluid particle moving down the center line of the nozzle. Solution. The acceleration following a fluid particle down the center line of the nozzle is to be estimated. Assumptions. The flow is steady and incompressible. The x direction is taken along the center line of the nozzle. By symmetry, v is equal to w is equal to 0 along the center line, but u increases through the nozzle. Analysis. The flow is steady, so you may be tempted to say that the acceleration is 0. However, even though the local acceleration, partial derivative of the velocity vector over the partial derivative of time, is identically 0 for the steady flow field, the advective acceleration, the velocity vector and dot product and del operator dot product times the velocity vector is not 0. We first calculate the average x-component of velocity at the inlet and outlet of the nozzle by dividing volume flow rate by the cross-sectional area. Inlet speed is 1.95 feet per second. Similarly, the average outlet speed is 10.4 feet per second. We now calculate the acceleration two ways with equivalent results. First, a simple average value of acceleration in the x direction is calculated based on the change in speed by an estimate of the residence time of a fluid particle in the nozzle, delta t equal to delta x over u average, figure 4-10. Residence time delta t is defined as the time it takes for a fluid particle to travel through the nozzle from inlet to outlet. By the fundamental definition of acceleration as the rate of change of velocity, method A yields acceleration in the x direction is equal to delta u over delta t, which is equal to u outlet squared minus u inlet squared over 2 times delta x. The second method uses the equation for acceleration field components in the Cartesian coordinates, equation 4-11. Here we see that only one advective term is non-zero. We approximate the average speed through the nozzle as the average of the inlet and outlet speeds, and we use a first-order finite difference approximation for the average value of the derivative partial differential of u partial differential of x through the center line of the nozzle. The result of method B is identical to that of method A. Substitution of the given values yields the axial acceleration equal to 160 feet per second squared. Discussion. Fluid particles are accelerated through the nozzle at nearly 5 times the acceleration of gravity, almost 5 g's. This simple example clearly illustrates that the acceleration of a fluid particle can be non-zero even in steady state. Note that the acceleration is actually a point function, whereas we have estimated a simple average acceleration through the entire nozzle. Material derivative. The total derivative operator d dt in equation 4-9 is given a special name, the material derivative. It is assigned a special notation, capital D over capital D t, in order to emphasize that it is formed by following a fluid particle as it moves through the flow field, figure 4-12. Other names for the material derivative include total particle Lagrangian Eulerian and substantial derivative. The material derivative, capital D over capital D t, is equal to d dt, which equals the partial differential over the partial derivative t plus the dot product of the velocity vector times the del operator. When we apply the material derivative of equation 4-12 to the velocity field, the result is the acceleration field as expressed by equation 4-9, which is thus sometimes called the material acceleration. The material acceleration, the acceleration vector in the as a function of x, y, z, and t, is equal to capital D v velocity vector over capital D t, which equals d velocity vector over dt, which equals the partial derivative of the velocity vector over the partial derivative of t plus the dot product of the velocity times the del operator times the velocity vector. Equation 4-12 can also be applied to other fluid properties besides velocity, both scalars and vectors. For example, the material derivative of pressure is written as equation 4-14. Capital dP over capital dt is equal to dP over dt, which is equal to the partial derivative of p over the partial derivative of time, plus the dot product of the velocity vector times the del operator times p. Equation 4-14 represents the time rate of change of pressure following a fluid particle as it moves through the flow and contains both local, unsteady, and advective components, figure 4-13. The material derivative, capital D over capital dt, is composed of a local or unsteady part and a convective or advective part. Example 4-3. Material acceleration of a steady velocity field. Consider the steady incompressible two-dimensional velocity field of example 4-1. A. Calculate the material acceleration at the point x equals 2 meters, y equals 3 meters. B. Sketch the material acceleration vectors at the same array of x and y values as in example 4-1. Solution for the given velocity field. The material acceleration vector is to be calculated at a particular point and plotted at an array of locations in the flow field. Assumptions. The flow is steady and incompressible. The flow is two-dimensional, implying no z component or velocity and no variation of u or v with z. Analysis. A. Using the velocity field of equation 1 of example 4-1 and the equation for material acceleration components in Cartesian coordinates, equation 4-11, we write expressions for the two non-zero components of the acceleration vector. A of x is equal to the partial differential of u over the partial derivative of t plus u times du dx plus v times partial derivative of u over partial derivative of y plus w partial derivative of u with respect to z, which equals 0 plus 0.5 plus 0.8x times 0.8 plus the difference 1.5 minus 0.8y times 0 plus 0, which equals 0.4 plus 0.64x meters per second squared. And a sub y is equal to the partial derivative of v with respect to t plus u times the partial derivative of v with respect to x plus v times the partial derivative of v with respect to y, and w times the partial derivative of u with respect to z, which equals 0 plus 0.5 plus 0.8x times 0.8 plus the difference 1.5 minus 0.8y times 0 plus 0, which equals 0.4 plus 0.64x meters per second squared. And a sub y is equal to the partial derivative of v with respect to t plus u times the partial derivative of v with respect to x plus v times the partial derivative of v with respect to y plus w times the partial derivative of v with respect to z, which equals 0 plus 0.5 plus 0.8x times 0 plus 1.5 minus 0.8y times negative 0.8 plus 0, which equals negative 1.2 plus 0.64y meters per second squared. At the point x equal to 2 meters, y equal to 3 meters, the acceleration in the x direction is equal to 1.68 meters per second squared, and in the y direction 0.720 meters per second squared. The equations in part A are applied to an array of x and y variables in the flow domain within the given limits, and the acceleration vectors are plotted in figure 4-14. Discussion. The acceleration field is non-zero, even though the flow is steady. Above the stagnation point, above y equals 1.875 meters, the acceleration vectors plotted in figure 4-14 point upward, increasing in magnitude away from the stagnation point. To the right of the stagnation point, to the right of x equal to negative 0.625 meters, the acceleration vectors point to the right, again increasing in magnitude away from the stagnation point. This agrees qualitatively with the velocity vectors of figure 4-4 and streamlines sketched in figure 4-14, namely, in the upper right portion of the flow field, fluid particles are accelerated in the upper right direction and therefore veer in the counterclockwise direction due to centripetal acceleration toward the upper right. The flow below y equals 1.875 meters is a mirror image of the flow above the symmetry line, and the flow to the left of x equal to negative 0.65 meters is a mirror image of the flow to the right of the symmetry line.